hope I can stick to it. So thank you, Noel, for the introduction. Thanks to Noel and Ben for the invitation and for organizing all of this. Before I dive into this roadmap and try to start following things, let me point out that, I meant to drop this in the chat before we start, so I'm going to do it now. There's a link in the chat to my slides. Alternately, you can go into the main room in Sococo, and I trust you are seeing my Sococo now. Several days ago, I dropped a link to the slides in here, and now I don't know how to move it. So it should probably be in a different room like this one, where there's also a link to the PDF of the slides, because what I'm going to show you has fancier animations and stuff. But if you just want the PDF, there's the link in the room. You can follow it. But we are going to use this thing if it loads. It was loaded a moment ago. There we go. So one reason for sharing that link with you is that these are in a sense very bad slides. They have far too much detail. And if this were a standalone talk, what I'm about to do would be sort of very bad talk form, because I'm going to show a tremendous amount of detail on some of the slides, not talk about it, move very rapidly on, and trust you all to kind of work it out. And my reason for doing that is that this is not a standalone talk, and for a number of you, this is, meant to be an introduction to something where you are going to spend much more time working through the details later on. And so these slides are meant to be there as a reference to that you can come back to and look at some of those details of things that I skip over quite quickly during this initial talk. So that's the first thing I wanted to point out. The goal of the talk is to introduce a project that Dan Thompson and I have been working on over the last 10, 11, 12 years, whatever it's been. And my initial idea was, okay, let me tell you what this machinery is, how you use it, and the kinds of things you can apply it to. But after thinking about it a bit more, I decided that this event is not called Black Boxes in Dynamics. This event is called Big Ideas in Dynamics. And I want to tell you about the ideas that lie inside of this machinery, which is one of the reasons why there's going to be a lot of details. So, big ideas. What are the big ideas? Well, in each of the first 4 sections of the talk, I've tried to identify one big idea, which is labeled here with a particular keyword. And in that section, I'll explain what that keyword is meant to indicate. So the keyword associated to the first section, the first step, is equidistribution. More precisely, this idea that equidistribution is the thing that maximizes entropy. So if you watched the pre-talk, and if you didn't, I hope you go watch it later, then you saw this idea that if I have an experiment that has a certain finite number of possible outcomes, say D of them, and the probability of each is given by a probability vector, then associated to that probability vector, we have a certain quantity which we can call the entropy, and that's what's the formula written here. That can be interpreted as the expected amount of information you gain by observing the outcome of the experiment. And the fundamental inequality for probability vectors says that that entropy is less than or equal to the logarithm of the number of possible outcomes. That's the first half of the big idea. The second half of the big idea is that you get equality if and only if all of the outcomes are equally likely, so that you maximize the entropy exactly when all outcomes are equally likely and never any other time. In particular, if you look at all possible probability vectors and their corresponding entropies, there is a unique probability vector that maximizes the entropy. The desire to maximize the entropy, okay, you may ask, why should we want to maximize the entropy? One reason is that it corresponds to an assumption of maximum ignorance. If you have an experiment about which you know absolutely nothing going in, then you sort of expect to learn the most by doing the experiment. And the more you know going in, the less you should expect to learn. So maximum ignorance corresponds to maximum entropy. And that's maximized by a unique probability vector. All of this is really just a calculus exercise. not exactly a trivial one. You have to do some work, and if you ask me to do it right now, I would probably mess it up, but it is a calculus exercise. It's also completely static. There's nothing about dynamical systems so far. This is meant to be big ideas in dynamics, so where is the dynamics? So let's look at the basic questions in dynamical systems that correspond to this idea. Suppose we have a compact metric space and a continuous map on it. We may look at the space, we can consider all of the invariant probability measures. And every invariant measure, there may be a lot of them, in the systems we're interested in, there will be a tremendously large number of them. But everyone has a certain entropy associated to it. That entropy is a non-negative number. It admits the definition which you saw in the pre-talk, if you watched it, for symbolic systems. It can be interpreted as the rate at which you expect to gain information by watching the system evolve in time. English is not commutative. The fact that these two things are the same is the Shannon-McMillan-Bryman theorem. But let me not spend time dwelling on that. There is a second notion of entropy, which is the topological entropy. And we'll see a definition of it a moment later. For the moment, the important thing is that topological entropy is equal to the supremum of all of the measure theoretic entropies. That's the variational principle. And we are going to be interested in measures that achieve the supremum, that is, measures of maximal entropy. We're going to be interested in the question of whether such measures exist, whether there's a unique such measure, and what properties it has. Actually, I'm going to be interested in the first two. Getting into properties takes a little more work and more time than we're going to have. There are various reasons why this is an interesting question to ask. I'm not going to dwell on them very long. Some of them are listed here. One thing I do want to point out is that all of this machinery that I talk about can be generalized to study thermodynamic formalism and equilibrium states for other potential. And if you don't know what that means, don't worry about it. I'm not going to talk about it. You don't need to know what that means to follow the rest of the talk. That's just a comment for people who have seen those words before. So with these in mind, let's see what the story is in the sort of classical uniformly hyperbolic set. That is, think about a nocive diffeomorphism, or for purposes of most of this talk, a subshift of finite type. That you should assume that it's topologically transitive, or even better, topologically mixing. And under this assumption, there is a unique measure of maximal entropy. So you get positive answers to the questions of existence and uniqueness. And then you get lots of answers regarding this question of properties, mixing, K, Bernoulli, exponential decay of correlation. I'm not going to talk about those. What I am going to talk about is the question of how you prove existence and uniqueness. And there are at least two big approaches. The one I'm going to talk about originated with Rufus Vaughn back in the 1970s and involves the properties of expansivity and specification. Before I start talking about what that means, and it'll actually be a while before I define either of those, I do want to mention that there are alternate approaches to these questions of existence, uniqueness, properties of the equilibrium state. One of the most important ones involves the Ruel-Perron-Frobenius operator, which you can apply either via Markov partitions or via something called anisotropic Vaughn spaces. I will not say anything more about this in this talk, but I do want you to be aware that the story I'm telling you is not the only story. There's a parallel story that in some ways is much stronger. You can actually get stronger results out of this machinery, but there are also ways in which this other machinery is more difficult to apply, at least from my point of view. But I'm biased because I work more on this side. So let me tell you something about it, or at least about our motivation. So we'd like to study questions of existence and uniqueness of measures of maximal entropy for systems beyond uniform hyperbolic. Think of things like logistic map, Henon map, the Lorentz attractor, billiard systems, partially hyperbolic things. And I'm going to eventually try to describe a version of non-uniform specification, whatever that means, that can be used in this setting. And this is what I've developed with Dan Thompson. Those other approaches can be extended also. So there's different ways of going at this. There are lots of open questions that still remain to be resolved. On the right, I've listed some of the primary references for the approach I'm talking about. The one in bold, this is the one that's sitting in that other room in Sococo. That's the survey paper that is going to form the core of this project for those who are doing it. And I did want to mention one further reference, which doesn't look related at first glance, but is. At least it uses some of the same big ideas that I'm going to highlight here. And that's a paper of myself, Yasha Person, and Agnieszka Zelerovich, where some of the ideas in this talk about uniform counting bounds play a crucial role in the study of thermodynamic formulas. But I won't talk about that further either. There's this thing here saying some counterexamples. That's one of the slides where there are some details that you can look at later. All of this slide is therefore is to say that when we try to go beyond uniform hyperbolicity, I'm saying our goal is to prove existence and uniqueness. So I should mention some counterexamples to tell you that it doesn't always work. There are examples where you don't have where there's no existence. You don't even have a measure of maximal entropy. There are examples where you have multiple measures of maximal entropy, even though the system is, let's say, topologically mixing. Those examples are described here. You can look at them on your own time. We are going to move on past the first steps into the general principle that lies behind uniqueness. So the idea in that first section was that equidistribution is the thing that maximizes entropy. And now we want to look at the question of how you prove existence and uniqueness of a measure of maximal entropy. And the key word I've said is upgrade. So what's being upgraded? There are certain general estimates which are true for every shift space and every invariant measure, which involve some sub-exponential quantity. That is some quantity which is allowed to go to zero or to infinity, but has to do so slowly. There are various places in the proof where you have to upgrade that sub-exponential to uniform, that is uniformly bounded away from zero, uniformly bounded away from infinity. I'm going to identify those as they appear. I'm going to mention the main ones right now. But first, let's set some notation. So we're going to talk about shift spaces. Eventually, we're going to talk about shift spaces with the specification property. Eventually, I have to tell you what that is. But for now, just think about general shift spaces. That is a closed shift invariant subset of the full shift on D symbols. And in this setting, the topological entropy is quite easy to find. You look at all of the words of length n that appear in some element of your shift space. You count how many of them there are, the cardinality of the number of the set of words of length n. Take a logarithm, divide by n, and send it to infinity. That limit h is the topological entropy. And what this exponent, I call this an exponential growth rate because it means that the number of words of length n is approximately equal to e to the nh. Now, throughout the talk, when I write this approximately equal to sign, what I mean is that the quantities on the left and the right have the same exponential growth rate. In other words, if you take their ratio, which here would be this quantity Cn, the number of words divided by e to the nh, that is sub-exponential in this sense. Okay, so those are all equivalent. I'm just formalizing my notation just a little bit. Now, it's not immediately obvious why this limit exists. If you saw the pre-talk, you know why it exists, but I'll tell you again in a moment. But first, let me mention two other places where we do need to upgrade a sub-exponential to uniform. One is the Shannon-McMillan-Bryman theorem, which tells us something about any measure of maximal entropy. Actually, it tells you something about any ergodic measure, but I'm interested in the consequence for measures of maximal entropy, which is that if you have any MME and you take a word of length n, for most words, the weight that the measure gives, that MME gives to it, is approximately equal to e to the minus n. Now, remember what this notation means. There's some sub-exponential error allowed here. And this only holds for most W's. So this is a very imprecise statement, and I'm not going to make it more precise. I'm just trying to communicate the big idea behind some of the arguments. And after all, it's going to get improved in just a minute anyway. But I do want to point out that this reflects the big idea from the first section. That is, equidistribution is the thing that maximizes entropy. Because what this is saying is that most words of length n have about the same weight, e to the minus nh. That's equidistribution. And then from this, you can deduce something that I'm going to call the Katak estimate, which is that if you have some set that has positive measure for a certain MME, and you count how many of the cylinders of length n intersect it, that number has to grow like e to the nh. Again, this the actual Katak entropy formula is formulated for general ergodic measures, but it not necessarily MMEs, but it has this consequence for MMEs. And if you don't understand all the nuances of these two things, don't worry about it. I'm going to formulate stronger versions of them in just a couple minutes. So with that as the setting, I've pointed out three quantities, three places where I'm claiming we're eventually going to upgrade sub-exponential to uniform somehow. Some of that upgrading process can happen almost immediately. And this is what appeared in the pre-talk. The existence of the limit in the definition of topological entropy is a consequence of subadditivity via Fekete. So if you count how many words there can be of length n plus k, well, every such word split, you can just take the first n symbols, the last k symbols, and that gives you an upper bound on how many words, how many long words there can be. The number of long words is at most the product of the numbers of short words. So there's this submultiplicativity for the size of the language. When you take logarithms, you get a subadditivity property. And subadditive sequences are a setting in which there is this tool that is sometimes, but not always, called Fekete. It says that if you have a subadditive sequence like this, its linear growth rate exists. And that's the part of it that you hear the most often. But there's two parts of it. It's not just that the limit exists, it's that the limit exists and is equal to the infimum of these terms. So it's almost as if this is a decreasing sequence. In general, it's not actually a decreasing sequence, but it's close to being a decreasing sequence. And the fact that the limit is less than or equal to this quantity can be rewritten quite easily to say that the number of words of length n is at least e to the nh. Let me go back upstairs for a moment. The sub-exponential estimate was that the number of words of length n is on the order of e to the nh. And we've just improved that to give a uniform lower bound. That's the first upgrade of sub-exponential to uniform. We're going to need to do that same sort of thing several more times. I do want to point out that you can actually prove this directly in just a couple lines. So here's an argument of what happens if you take a word of length k and break it into blocks of length 1. And if you take a word of length nk and break it into blocks of length n, you get this upper bound, which is the same one I just proved here. This is actually how you prove Fekete's lemma. This plus a little bit more. And the consequence of all of this is that the uniform lower counting bound that I said we want, you get that for free. Now, if you want a uniform upper counting bound, you need more hypotheses, and we'll talk about that later. I should mention that in the definition of measure theoretic entropy, which is as a linear growth rate of the static entropy with respect to a certain partition, a partition into n cylinders, the existence of that limit is once again a consequence of subadditivity, Fekete's lemma, and you once again get a certain uniform bound, which is important in a particular place in the proof of uniqueness. But I don't think we should spend too much time dwelling on that right now. Instead, we should talk about what role all of this plays in the questions of existence and uniqueness. And we're going to start with existence. And actually, the answer is that in the question of existence, what I just said plays almost no role. So for an arbitrary subshift, it's possible to construct a measure of maximal entropy, basically using the first big idea, the big idea from the first section, that equidistribution maximizes entropy. So when Mizarevich gave a proof of the variational principle, he did so using a certain construction, which in the context of a shift space produces a measure of maximal entropy. And there's two parts to the construction. first is to say, we want to measure of maximal entropy, so, well, it should be equidistributed. That is, if I look how much weight our measure gives to cylinders of order n, well, they should all get roughly the same weight. So the number of them is the number of words of length n. Let's give each one a weight which is the reciprocal of that. And let's just consider any measure mn that does this. Okay, now that measure is probably not shift invariant, and we want shift invariant measures. So if you want a shift invariant measure, there is a almost canonical way to produce one, which is to start with any measure, push it forward and average, and then take the amount of time that you're pushing forward and averaging over, send that to infinity, and in the limit you get an invariant measure. That's kind of the standard proof of the Krylov-Bogoliubov theorem on existence of invariant measures. And combining these two ideas, it can be shown that any limit point of this process gives you an MN. Now, there's some work to be done here. It's a real argument. It's not at all obvious, but it's sort of plausible from the general principles. That's a construction of an MME for an arbitrary shift space. Going back upstairs for a moment. Once you have an MME, you have this Shannon-Millen-Breiman theorem, which says that the measure of most words of length n is on the order of e to the minus nh. Well, we need to upgrade that to uniform somehow. It turns out that for a subshift of finite type, there's an alternate construction of the measure of maximal entropy that gives you a uniform bound quite directly. So if you have ever seen something called the Perry measure, this is something that you can build for a subshift of finite type using the eigendata of the transition matrix. That's algebraic information that is not present for an arbitrary subshift. And so you're really working in a more restricted class there. But this construction gives you a measure that has this stronger property, that is the measure of a word of length n is bounded below by a constant times e to the minus nh. So once again, sub-exponential has been upgraded to uniform. There's also a corresponding upper bound, but we don't need it for what comes later. For now, let me just mention that if you wanted to, and this isn't written, and I should have put it here, I put it later on. Suppose you wanted to prove a corresponding uniform bound. This is called a uniform Gibbs bound. Suppose you wanted to prove that for the measure coming from the Mizurevich construction. Well, then you would try to prove it for these measures mn and their push forwards. So you try to prove it for these measures that occur in the average here. And if you want to know how much weight these guys give to a word W, what that question really amounts to is asking, out of all of the words of length n, how many such words see the word W starting in position K? So it reduces to a counting question. And if you can get good estimates on that number, then you can get good estimates on mu of W. And that's the strategy for proving the lower Gibbs bound later. But don't worry about it too much for now. I'm just mentioning it because the construction is on the screen right now. So the point of this slide is just that there is a construction of an MME that works in general, and that for mixing subshifts of finite type, you actually get this stronger uniform lower bound, so that you've now managed to upgrade two of the three a priori quantities that I started off with. So there were three things. There was the topological, there was the number of words, there was the Shannon-Millen-Breiman, and then there was the Katak estimate. We'll come back to that third one. But now I'm in a position where I can outline for you how the proof of uniqueness goes. And there's definitely going to be some a lot of details hidden on this slide. So I'm trying to identify the utility of that upgrade in this process rather than communicate all of the things in the argument. But the basic idea behind proving uniqueness is actually fairly simple, and it's what's written on these first three lines. The general principle, the big idea from the first section, was that any MME should be roughly equidistributed over words of length. Well, if you have two measures like that, it's reasonable to expect them to be mutually absolutely continuous, that is, equivalent to each other, that that they should not be singular. You shouldn't have a set which has full measure for one of them and zero measure for the other if they're both giving kind of equal weight to all n cylinders. That's a very hand-wavy, rough idea that's quite far from being an actual proof. But if you could prove that, more precisely, if you could prove that you have an ergodic MME with respect to which any other MME is absolutely continuous, then those two measures would actually have to be equal. This is an exercise in ergodic theory. It's actually a pretty straightforward consequence of the definition of ergodicity. If you have an invariant measure absolutely continuous with respect to mu, then you look at the Radon-Nikodym derivative. The fact that both of the look at the Radon-Nikodym derivative, that ends up being a invariant function, which by ergodicity must be constant almost everywhere. Therefore, the measures have to be the same. And that reduces the proof of uniqueness to checking this absolute continuity. So the goal now is absolute continuity. I start with an ergodic MME, such as the Perry measure that I claimed can be constructed for subshifts of finite type. And suppose that I somehow know that it satisfies this uniform Gibbs bound. And that's all I know about it. I know that it is ergodic, a measure of maximal entropy, and that it satisfies the lower Gibbs, this uniform lower Gibbs bound. Then, okay, here's the spoiler. The end of the story is that it is the unique MME. So that's the mechanism for uniqueness. And what's written at left here is the structure of the proof. The first observation is that if you have this lower Gibbs bound, so you know every word gets at least a certain weight, then that puts an upper bound on how many words there can be. Because it's just reciprocal. You add up all of the weights, they have to add up to 1. So the number of them is at most reciprocal of c times e to the nh. That's a uniform upper counting bound to complement the uniform lower counting bound we got for free a little while ago. If you have this uniform upper counting bound, it turns out that you can get a uniform Katok estimate. This is really a crucial part of the proof, so I do want to highlight it, but it's also a fairly detailed one, so I don't want to dwell on it. Basically, what it means is that it gives you information that applies to an arbitrary measure of maximal entropy. Suppose I have some set, and I cover my set by a certain number of n cylinders. Then I get a relationship between the number of n cylinders that it takes me and the measure of that set with respect to an arbitrary MME. The formula is not particularly important. There is a proof of this fact on a slide that I am going to not spend any time on, apart from one thing. The only thing I want you to observe about this slide, or rather to listen to me telling you, is that everything here is just general properties of entropy, except in one place, right here, where we use the fact that use an assumption that the number of words of length n admits this uniform upper counting bound. So the fact that we were able to upgrade sub-exponential to uniform for the number of words of length n leads to a corresponding upgrade for this other thing that's important. Now, if you are doing this project, by the way, and you're reading that survey paper or any of the original literature, the argument as I've written it here is a little bit different from those, and that's one reason I wanted to include it. I think this way of presenting it highlights the role of the upper bound just a little bit more clearly. But we shouldn't dwell on it right now. The only thing that it's needed for in the proof of uniqueness is to combine with this uniform Gibbs bound. And why would we be doing that? Why are we combining these things? What was the strategy? The strategy that I said was to take an ergodic MME and prove that any other MME must be absolutely continuous with respect to it. That is the goal. To do that, we assume we have some set which has positive measure for an arbitrary MME. Then you have an estimate on how many n cylinders intersect that set. You have an estimate on the mu measure of each of those cylinders, and if you combine those, you get a certain formula which guarantees that that set has positive measure with respect to mu. I went through that far too quickly. to claim that I've explained the details, but I hope I have explained the skeleton, the structure, which is that the proof of uniqueness has this form. Those three estimates, which a priori for an arbitrary subshift are just sub-exponential, can, in certain contexts, such as mixing SFTs, be upgraded to uniform estimates. And then the uniform counting bounds imply a uniform Patak estimate, which together with uniform Gibbs bound gives uniqueness. Once you put all that together, that's a complete proof that a mixing subshift of finite type has a unique measure of maximal entropy. But the proof relies on getting the uniform Gibbs bound from these algebraic considerations. And I want to avoid that. I want a different argument. So let me explain the general principle behind getting the uniform counting bounds via the specification approach, which is going to lead me to actually define the thing that this talk is supposed to be about, only, a little over 2/3 of the way through it. So the first half of this is exactly what I mentioned when I explained why the topological entropy exists. It's almost verbatim the same. The fact that submultiplicativity of the size of the language, the number of long words is less than or equal to the product of the numbers of short words, lets you use Feket's lemma, lets you get this uniform lower count. To get a uniform upper counting bound via this kind of argument, you would need to reverse the inequality. That is, instead of saying that the number of long words is less than or equal to products of the number of short words, I would need to go the other way. I would need to say that given words of length n and words of length m, I can always put them together to make words of length n plus m. If you're in the full shift, you can do that. But if you're in the full shift, you're the full shift, and you kind of know it's very easy to simply write down what everything is. In general, this is just far too small. And what you can do instead for a mixing subshift of finite type is get this almost supermultiplicativity estimate. And here's the property of mixing SFTs that lets you do it. Think of a mixing subshift of finite type as being given by a directed graph with finitely many vertices. The fact that it's mixing means that there is a certain natural number tau, such that if you give me any initial symbol and any other symbol, and you tell me to start on the initial symbol and get to the other symbol in exactly tau steps along this directed graph, I'm able to do it. There's also a way of writing that down in terms of the transition. And as a consequence of that, if you give me any two words, V and W, in the language of my mixing SFT, then I can look at the last word of V, the last symbol of V, the first symbol of W, find a path that takes me from the last symbol of V to the first of W in exactly tau steps. I can label that path by a word U in the language of the shift, which has length exactly tau, and then V followed by U followed by W is in my language. So this gives you a way of gluing words together, provided you're allowed to put a gap in the middle of length exactly tau. And the really crucial thing here is that the length of this is equal to tau no matter how long V and W are. If you just require that there's some word and you don't care how long it is, that's the definition of topologically mixing for a general subshift. So it's really the fact that it's a mixing subshift of finite type lets you upgrade that to this. And this is what I'm going to call the specification property in a moment. Let me, for the moment, but first just mention that this is what gives you a way of getting the upper counting bound, because by gluing things together, you can get a lower bound on the number of long words in terms of numbers of short words. And then similar arguments give you the upper bound. So I said that this is a specification property, so let me repeat it here. This is exactly what I wrote down on the previous slide. And the argument that I waved my hands through there is an argument that mixing subshifts of finite type have a specification property. And that the specification property gives you uniform counting bounds, both lower and upper. That is almost what you need for the proof of uniqueness. Uniform counting bounds gives you the uniform talk estimate, then you need a uniform Gibbs bound, and then the argument runs. But where should the uniform Gibbs bound come from? Well, remember a few slides ago when I was describing the Mizraevich construction, I pointed out what you would need to do in order to get a uniform lower Gibbs bound. You would need to get estimates of the number of words of length n that see a given word starting in a certain position. And I'm not going to say anything more about the proof than that, but that reduces the problem of constructing a Gibbs measure to getting good counting estimates. And once you combine all of that, you end up with Vaughn's theorem that every shift space with specification has a unique measure of maximal entropy. Okay. So I hope I explained how the idea of upgrading sub-exponential to uniform in multiple places plays a crucial role in the proof of uniqueness. And now, having spent 36 minutes of my time, I am 40% of the way through the sections, but that's okay. The main thing really was to communicate this. In my mind, this is the most important big idea, and everything after it is kind of questions of how do we import the big ideas from these first two sections into broader settings. And for the moment, I'm going to remain in the setting of symbolic systems and talk about this idea of obstructions. That is, I'm going to talk about a way to make precise the idea of obstructions to specification. So if the shift has specification, then Vaughn had this theorem saying that there's a unique MME. There's plenty of shift spaces without specification that were known to have unique MMEs and that turn out, in retrospect, to have a certain non-uniform specification property. And this is what Van Thompson and I developed. The initial applications were beta shifts and S-gap shifts, but just by way of putting things in a broader context, since I am almost certainly not going to have time to say anything substantial about it, there are applications of the general principles to smooth systems. So things like geodesic flow and non-positive curvature, things like the Lorentz tractor, other examples as well. But I'd like to communicate the big idea behind this extension from uniform to non-uniform. And the crucial idea is this idea of a decomposition of the language. So suppose we have a shift space and L is its language. So that L is all of the possible finite words that appear in any sequence in your shift space. By a decomposition of the language, I mean a choice of three lists. A list CP, which you should think of as prefixes or prefix constraints. A list G of words, which you should think of as good words, and a list CS, which you should think of as suffix constraints. And formally, the definition of decomposition is what's written here. Informally, what it means is that if you give me any word in the language of the shift, I can look at that word and find a good core, a good word that's inside the word you gave me. And I can get to that good core by removing a prefix, which comes from the prefix collection, and a suffix, which comes from the suffix collection. So I can strip some symbols off the front, they're in the prefix collection. I can strip some symbols off the end, they're in the suffix collection, and the stuff in the middle is supposed to form a good word. We say that the collection of good words has specification if, well, it's the same property as before, except you have to be able to glue together good words. So there needs to be some tau, and I often would call tau a gluing time or a block size, because you think of it as how long you need in order to glue together different words, or how much of a gap you need to leave between different words when you glue them together. And you need this tau to have the property that if you give me any collection of good words, I can find connecting words of length exactly tau, such that the whole thing put together is legal, is in my language. So the idea is that you should find a decomposition such that You have a collection of good words, and you need that collection to be large enough. And the way to make that, to formalize the notion that G should be large enough, is to require these prefix and suffix collections to be small. And what I mean by small is that they have smaller entropy than the whole system. So entropy is an exponential growth rate of the number of words. So what I'm going to do is I'm going to take the number of prefix words of length n, the number of suffix words of length n, I'm going to take the logarithm of that, divide it by n, send n to infinity, take a lim sup, call that the entropy of obstructions to specification. And ideally, what I would like is to have a decomposition where G has specification and the entropy of obstructions is smaller than the topological entropy of the whole shift space. And in fact, the theorem on the next slide will say that in this setting, you do in fact have a unique measure of maximal entropy. But first, I should mention an example of a decomposition. One example is with the beta shift, and in the survey paper describes that in some detail. The S-gap shift is maybe a little quicker to present. So the S-gap shift is what you get if you specify a set of natural numbers called S, which tells you which length of strings of zeros are allowed. So it's a space of bi-infinite sequence of zeros and ones. And anytime you see two ones with a string of zeros in between them, the length of that string has to be something from S. And then your good words are things that have complete legal strings of zeros. And your prefixes and suffixes are things like this that may or may not be complete. So it's a decomposition because any word in the language you can be split up into an initial string of zeros, followed by a bunch of completed blocks, followed by a suffix, which is just a partial block. And there's exactly one prefix of any given length, and there's exactly one suffix of any given length. So this number grows sub-exponentially, and you have entropy 0 for the obstructions. So that's an example which I hope illustrates the process. Okay, I said the uniqueness theorem is on the next slide. It's not, because I'm trying to get to the big idea. And the big idea is that if these obstructions have small entropy, you still get the uniform bounds that were key to the uniqueness argument. So there's a computation on this slide. The computation is details that is there for you to look at later if you want to see what's really going on here. The assumptions are that you have a decomposition where G has specifications, so you have these good words, and then the obstructions, the prefixes and suffixes, carry small entropy. You can still use a lot of the earlier proofs of uniform counting bounds. Remember that lower counting bound on the number of words in the language, that always applies to an arbitrary shift space. So it works for the S-gap shifts. And that upper bound on the number of words, well, it still works if you use it for the number of good words. Now, the number of good words might be smaller than the number of total words. So you glue good words together and use the specification argument to get this uniform upper bound on the number of good words. And then your goal is to upgrade it to a uniform upper bound on the total number of words. And that's where this entropy gap condition comes in. It's a computation involving infinite sums. You can read it and look through it. It's not particularly long. It's also, I think, not too informative if I try to walk you through all the details right now. But let me highlight one place where things do get more complicated. So here I've kind of given the impression that as long as you have a decomposition with the specification property and this entropy gap, everything's just fine. You can just repeat the original proof. You still get the uniform counting bounds, and you run the uniqueness argument exactly as Vaughn. It's not quite that simple, because when you try to prove this uniform lower Gibbs property, which was the other crucial ingredient for the uniqueness argument, you don't actually get a uniform Gibbs property out of this. What you get is you get a Gibbs bound for the Mizraevich MME, but you only get it for good words. You get a lower bound on the length of words that lie in your, on the weight of words that lie in your good collection G. So bear that in mind. as I spend my last 5 minutes saying something about the uniqueness argument, or maybe hopefully not quite that much, so I can point at the last sections of the talk, or the slides rather. So here's the theorem. I alluded to it a moment ago. If you have a shift space whose language admits a decomposition, where the good words have specification and the prefix suffix collection carries smaller entropy than the whole system, then there's a unique measure of maximal entropy. I should mention that when Dan and I originally proved this, we required an extra condition, which was very annoying, and I don't like it, so please don't look at it because you don't need it. There's a recent improvement of this result due to Zeze Pacifico, Fan Yang, and Jiagang Yang, where they gave an argument showing that you can actually remove this extra condition and prove the theorem as it should be. To explain what they improved, let me point out the general structure of the proof. And by the way, I have a blog post. If you're really interested in the guts of that improvement, I have a blog post from this last summer that explains exactly what's going on there. But what's the structure of the proof? Okay, this part of it is kind of the same as in the uniform specification case, right? You get uniform counting bounds, which in our case can be deduced from the assuming that obstructions to specification have small entropy. That leads to uniform counting bounds via the computation that I showed you and then ran away from. From those, you deduce the uniform Katak estimates via another computation that I showed you and then ran away from. Those together with the specification property that let you construct an MME that has the Gibbs property on good words, on good cylinders. And the idea of the last step of the proof was to run the absolute continuity argument. That is, take your Gibbs measure, take any other MME, show that that MME must be absolutely continuous with respect to the Gibbs measure. And the way to do it was to approximate an arbitrary set Z by a union of n cylinders and then use the Gibbs property. But if you only have the Gibbs property on good cylinders, well, then the cylinders that you are approximating with had better be good ones. And that's really, that's a sort of annoying technical part in this proof that we resolved one way, Dan and I did, by adding an extra assumption. And these guys found a better way to resolve it that does not require that extra assumption. So there's the very short version of what they improved, how they improved things. So that's the theorem for shift spaces. And hopefully I communicated something about the big idea that you want your obstructions to the uniform classical property to have small entropy relative to the whole system, and then you can still deduce the uniform bounds. Those uniform, the fact that you can upgrade those uniform bounds is what gives you the uniqueness. And then if you want to apply this to things like diffeomorphisms and flows, you have to get a non-symbolic version of that. Now, I am essentially out of time, so let me just say what the big idea is here. I'm almost out of time, and I've just come to a slide on which there's a section called the guts of the proof. So that is probably good news for all concerned. The big idea in this section is that all of those symbolic ideas, there's kind of a dictionary that lets you take the symbolic ideas and the symbolic arguments and run them in the non-symbolic set. And if I'd really been on the ball, I would have found that dictionary for you explicitly here. Instead, it's just sort of interspersed throughout these slides. The idea is that instead of working with the language, you work with the space of finite length orbit segments. Anytime you see a cylinder, you talk about a bowling ball, unless that cylinder is meant to be part of a partition, in which case you talk about an adapted partition. When you look at the set of words of length n, sometimes you have to talk about an maximal n epsilon separated set. There's this correspondence between the symbolic world and the non-symbolic world that lets you take symbolic arguments and adapt them in a way that becomes almost automatic. And to the point where, right now, Dan Thompson and I and his former student Tianyu Wang are working on adapting all of this machinery to the non-compact setting. And one of the things that we've done in order to do that is first write everything down in the symbolic setting and then run it through this dictionary, because it's just so much easier to write things down in the symbolic setting first, which is why I started there to present this. In order to run that dictionary, there's an essential thing. You have to be able to work at a fixed scale, and that's where there's an assumption called expansivity that comes in. You then have to say that obstructions to expansivity are small, but I'm out of time. So let me simply point out that there are lots of applications of this that various people have developed. Some are symbolic, some are in partial hyperbolicity, some are in non-uniform hyperbolicity, and there's quite a few in geodesic flows, up to and including very recent work by our two organizers here and some co-authors. So, and there's a great deal, I think, that can still be done with it. So it is by no means played out. And I think that's a place for me to end the talk. And thank you very much for listening.
Thank you for that great talk, and also these slides, which will selfishly be very useful to me after. Does anybody have questions they'd like to ask? Okay, I was just giving it a little Zoom delay. Okay, my question for you, Vaughn, is like, what was the most difficult part of learning how to do this? Right? Like, like what do you recall being the worst part?
You remember how I had a slide entitled "The Guts of the Proof"?
Yes.
That's not particularly pleasant. Let me, now I have to remember how to move through this. There we go. Beyond symbolic news. Yeah. So when you try to run this in the non-symbolic setting, a lot of stuff happens that forces you to work at different scales. So sometimes we're working at scale epsilon, sometimes it's 2 epsilon, sometimes it's 6 epsilon, sometimes it's really sort of a technical, irritating bookkeeping thing, but that dictionary really is it's annoying and time consuming to run things through. And that's something that we encounter at every sort of new iteration of the process. So I would say for me, certainly that's the most irritating part, is having to run things through that dictionary and do all of this. But fortunately, I think the bright side of that is that the symbolic version of it really does illustrate so many of the basic principles that you can get a very long way by working in that symbolic setting and then sort of pushing things through and enduring the pain. But the dictionary is reliable enough that once you have it in the symbolic setting, you can be pretty confident that it's going to.
Thank you. Right, I want to double check to see if there are any other questions. All right, let's thank Vaughn again.
Thank you.
I think Ben and I just want to follow